So, hi everybody, my name is Michele Garraffa, and I will talk in this presentation about hybrid approach, mixing meteoristics and Gaussian programming for a scheduling problem. That is the hybrid flexible Flowshop with transportation times. So this is joint work with the Armstrong from Johnson Research Center, Barry O'Sullivan, and Helmut Simonis from University College Cork. So this is the outline of the presentation. It's formatted by 4 different parts. In the first part, I will present the problem definition and try to collocate the problem in the state of the art. In the second part of the presentation, I will describe mainly 3 approaches to solve the problem, so Gaussian programming, meteoristics, and hybrid heuristics. In the third part, we will see how actually this approach perform. So I will present some computational results. And finally, I will give some conclusion and directions for future work. So the problem that we studied is an extension of the hybrid Flowshop problem, which some of you may be familiar with. Let's consider a set of jobs, a set of machines, and a set of production stages. So each machine belongs only to one stage, and each job requires a processing time to complete each stage. So this does not depend on the machine where the job is processed. Each job can also skip some of the production stage. This is an information that we know a priori depending on the type of job. A certain transportation time is required to move a job from one machine to another, and this transportation time is machine dependent. So it depends only on the two machines involved. So we don't consider limitations on the buffer and on the number of transporters, and we strive for minimizing the mixspan. So in this picture, you can see basically the structure of the production floor that we are considering also in our instances, where the machines are disposed in a matrix, and this represents the physical locations of the machines. So the jobs start at the left, they are processed by one machine per stage, and so the production is completed after completing the last stage. So in these slides, as I was mentioning before, we can see that if we don't include the stage skipping and we don't include the transportation times, so if we consider 0 transportation times, the problem is reduced to a hybrid Flowshop problem, which is a well-studied problem in scheduling. In this review from 2010, published in the European Journal of War, you can see that already in 2010 there were many studies regarding this problem. So the problem, so the hybrid Flowshop problem is NPR even in many of its restrictions. And so if you think about one machine per stage, at the case with one machine per stage, that is basically a Flowshop problem. If we consider stage skipping, but we don't consider transportation times, in this case we have a hybrid flexible Flowshop, which is surely less studied. And here I'm reporting a reference with basically MILP models, different MILP models of the problem. And the problem I will talk about in this presentation is basically the same that with the same models. So we published in CP 2021, and in this so this is the only previous study using exactly this problem definition. I have just a couple of tables to give you just a general idea of the fact that there are even pretty old studies studying, including transportation times in scheduling. So here I have a slide with Flowshop problems and another slide with other scheduling problems, so the different, for example, open shop, job shop, and so on. But in our state-of-the-art review, so when we were looking for different problem definitions, none of them were exactly matching our, maybe because of the type of transportation times, the type of production floor, and so on. So I think as the first thing that we started doing when we started studying this problem, it was formulated in terms of mixed interlinear programming. And there are 4 MLP formulations that can be pretty easily obtained by modifying the formulations in Dairy's paper, the one that I mentioned a few slides ago. And they perform very bad because of the poor quality of the linear relaxation, because of the logical constraints involved, and these models were able to solve only instances of very small size. So then we tried with constraint programming, and that is one of the things that I will describe in the next few slides. And then we studied the meta heuristics based on forward scheduling and guided by reference permutations. This is a kind of no, there are many papers doing something similar for the hybrid Flowshop problem. So we kind of adapted that from the state of the art in a sense. And then we developed some hybrid heuristics, hybridizing the last 2 methods that I mentioned. So let's give a quick look at the constraint programming model. So this constraint programming model is based on the CPAIOR optimizer library. There are, of course, other type of formulations that you can adopt here. So there are 3 sets of variables, interval variables related to each job and a machine, interval variables related to each job and stage, and integer variables keeping track of where each job is executed at each stage. And then here we use this notation for the next stage, and we use this notation, so this delta m prime, to basically identify the transportation time between one machine and another one. As you can see here, we are considering only machine-dependent transportation times. So we want to minimize the max panel, that is the completion time of the last job. And then we have this set of constraints. The first is the linking constraints between the machine variables and the interval variables related to the machines. Then we also have to link the 2 sets of interval variables, the one related to the machines and the one related to the stages. We have kind of classical Flowshop constraints saying that a job at a certain stage can start after being completed at the previous stage. Then we have an overlap constraint on the same machine, saying that our machine cannot, of course, process 2 jobs at the same time. And then we have redundant and cumulative constraints. Okay, here I want to try to give a quick overview of the meta heuristic approach that we implemented. So the approach is basically is an adaptation of the one developed in this paper. What we changed is this is a reference from 2019. But usually for the hybrid Flowshop problems, they consider instances up to 100 or 150 jobs. So in here, we needed a little bit more scalability, because for the experiments that we will see, we will go up to 400 jobs. So we replaced the constructive approach to generate an initial solution with the well-known NEH heuristic, just to have quickly a good solution to start with. So the approach is an iterated greedy approach based on forward scheduling, where this means that the solution is encoded by means of a permutation. And then there is a greedy rule that is basically able to map this permutation into a full solution. So the jobs are first scheduled by following the order in the permutation at the first stage. And then they are scheduled according to the release time order in the other stages. So the greedy rule that is used is that they are scheduled as early as possible at the earliest available machine. And here we need to take it into account in our adapted version of the transportation times. So the local search approaches are still based on the permutation. There is this RIS and RSS that they are basically two types of local search based on insertion, so kind of one-opt, and swap, and swapping the jobs in the permutation. So this is the general scheme of this iterated greedy approach. We start with an EH. Then we start a loop that we repeat until a certain time limit is achieved. There is a deconstruction-reconstruction procedure to escape local minima. The two local search approaches are run with a certain probability. There is a certain probability to accept the current solution or not. And this loop, again, it iterates until the time limit is reached, and we keep track of the best solution. So how can we hybridize these two approaches? So we start by running the heuristic for half of the time limit, and then we fix the solution up to a certain stage. So then we run the CP model by fixing a part of the solution on the remaining user problem. So this is a kind of stage-based decomposition that we used, and that is that you will see the results regarding this. But since the submission, we also worked on other types of decomposition that may be interesting in this context. For example, decomposing according to the job and not the stages. So computational results. So we consider that, so this is this problem is basically the problem definition and the instances. They are defined according to the guidelines of the industrial partner. And we generated the instances in this way, so following the guidelines, so with 8 stages, 10 machines per stage. Some stages are skipped. Then the number of jobs changed from 20 to 400. We generated 25 instances per problem size. We have basically this concept of job type, saying that job of the same type, they have all the same processing times. And we generated such that there are a few products that are quite common and others that are pretty rare. And the transportation times, as I was saying, basically they are generated in order to represent a lanes scenario. So the case where the metrics are disposed in a matrix. So the physical location is in a matrix, and the transportation time is proportional to the distance. So these are the results published in the paper. So we basically have 2 tables, one with the average objective value and one with the average percentage cap. So for each line that you see in these tables, it's the average over 25 instances. So the first approach is the constructive NEH heuristic. Then we have the iterated greedy with half of the time and with the full time limit. And then we have 3 versions with a different number of stages fixed. Then these are the results from our CP 2021 paper, and these are the lower bounds. So the time limit that we adopted is 300 seconds. So as you can see, given the time limit of 200 seconds, in almost most of the cases, the hybrid approach with 4 stages fixed achieved the best results. And the only, apart from the very small instances where this is kind of I think it's pretty reasonable, because in this case we just fix half of the stages. So the other case is with 300, where it doesn't perform, it doesn't achieve the best performances. So basically, for this reason, I have this other slide trying to show the fact that for 300s, the iterated greedy had a very high average sum of square deviation of the results. So this indicates the fact that it didn't. So basically, it's the results that we get. They are very much oscillating, and that means that basically for the time limits adopted for these instances is too short, and the iterated greedy has still a lot of margin of improvement. So if when we run with a higher time limits of to 2400 seconds, basically we can see that we achieve all the best results for all the instance sites. So in this table, in this graph, you can see that the results provided by the iterated greedy, the hybrid approach, when the time changes from 0 seconds to 1000. So as you can see at the beginning, the hybrid approach achieves worse performances than IGT, than iterated greedy, and then at some point it outperforms the iterated greedy method. So this is an example with 100 jobs. These are something extra, not included in the paper, but this is just to give you a general idea about what happens when we consider 0 transportation times. So in this experiment, we just consider 300 seconds. To simplify everything, I'm considering 300 seconds, and I'm considering a hybrid as a version where it runs on top of the iterated greedy with Tmax and half of extra time. So as you can see from these results, it's basically the method is able almost always to improve the results of the iterated greedy. And yeah, these are the best results are indicated in bold. And this basically gives us a kind of a feeling that these kind of decomposition and probably also other types of decomposition, that they can work well for our problem, but also for the hybrid flexible Flowshop. So conclusions and future work. So sure, in our the reason why we get good results is the fact that we exploit the complementarity of the two approaches. For sure, hybrid gets better results than the CP model and the iterated greedy, with the cost of having a little bit of more of development effort. Then we are very much interested in working on other decomposition heuristics, because it seems like, especially for large instances, both of our problem, but also for the hybrid Flowshop problem. It seems like this type of decomposition heuristic and decomposing the problem is another way. It brings to strong improvements. This is basically due to the fact that the iterated greedy methods for hybrid Flowshop, they are permutation based, and that basically they reconstruct solutions from scratch. And that when you go up to the sides, then they don't scale well. So we have been working in the last few months on this new type of decompositions. And then I think it will be interesting to test the approaches on standard data set with and without, by adding transportation times or with 0 transportation times. And we think also that it will be an interesting research direction to refine our problem definition as well. Thank you for your attention.
Thank you. Yes.
How many jobs you can have simultaneously at each stage in your benchmark?
Did you hear the question?
How many jobs you can simultaneously have for each stage.
No, there are no limitations on the number of jobs that we can execute at the same time at each of the stages. So there are no constraints related to this. There are no limitations.
Okay, maybe one more quick question.
Did you try large neighborhood search methods for this problem?
So the question is, did you try large neighborhood search?
So it's I would say that with the large neighborhood search we mean it depends on what we mean with large neighborhood search. In general, I would say that an iterative version of our method could be seen in that way. So I will say that for this specific problem, there is no hope for a large neighborhood search based on MLP for exploring the neighborhood, because because the MLP model, they're not performing well even with very small amount of jobs. So, and I think the reference for this, a good reference for this model is this Naderi's paper.
Okay, let's thank the speaker again.